the lecture. Okay, good. So for those of you who are joining in, we're really only on the first slide. If you're joining recording, I'm reminding everyone that the test is April 22nd, which is the first Tuesday back from spring break. No, not the 22nd, I'm sorry. That's April 21st. Tuesday, April 21st is the exam. Again, that is Tuesday, April 21st. Okay? All right. So, and again, it'll be on Wiley Plus. We'll work that out. But getting back to this, let's draw some free body diagrams. So at first, they're simple, right? You just draw a dot here. Fn and Fg. Okay? So there's only two forces, and you'll remember the frictional force is 0 because in order to have a frictional force, you must be in order to have a frictional force, you have to be accelerating somehow. Right now, the box is not accelerating, and there's no force being applied to it. So one of those conditions has to be met, at least for static friction, right? For static friction, you have to apply a force. For kinetic friction, you don't need to apply a force, but you need to be moving, right? You need to have some velocity and then be accelerating. In this case, for static friction, you have to have an applied force. You'll notice here, you have that applied force, and friction starts to build up. And now the free body diagram looks like this. We still have Fn. We still have Fg. You'll notice the force is being applied to the left, and the friction will oppose the motion. And now going down here, I make the free body diagram again. Seems redundant and it seems tedious, but there's a reason to do this. This is our max Fs. We'll call this Fs max. We'll call this F. All right, and that is that if you want to apply Newton's laws, you want to sum the forces in the x direction and sum the forces in the y direction. Use Newton's second law to set up your equations, but you have to, in order to sum the forces, you just go around a free body diagram and ask if the force is in that direction. If it is, you add it and you put the proper direction. And that's all there is to that, really. All right? This is how we do these types of problems. But the best way to do it is to practice it. So let's take a look again. At static friction now. So the static friction, when it starts moving, the static friction isn't variable, or the kinetic friction isn't variable like the static friction. All right, so now we're in that kinetic regime, and you'll notice the force can shrink. All right, and that took us to our example that we ended on, right, with the car. And you'll recall also that Fs max mu k. That's an unfortunate. Equals mu k. Oh, right. I need to go back to. Sorry, mu s. Fs and Fk equals mu k times Fn, and that's a mistake, so I'll fix that. Okay, now that's all correct. So remember, the frictional force is dependent on this coefficient of friction, either the static or kinetic, depending on which friction you're talking about, or it is dependent on the normal force, okay? So, well, they're both dependent on the normal force. It's the static, or it's the coefficients that change. And the coefficients are unitless and will depend on the material. You'll either be given those, or you'll have to solve for it, or you'll have to look it up in a table. We did this yesterday. And now we want to move on to a different example. This sample problem will involve a tilted applied force, which requires that we work with components to find a frictional force. The main challenge is to sort out all the components, so this can get challenging. Figure 6.3a will show a force of magnitude of 12 newtons applied to an 8 kilogram block at a downward angle of 30 degrees. The coefficient of static friction between the block and the floor is 0.7, and the coefficient of kinetic friction is equal to 0.4. So does the block begin to slide, or does the block remain stationary? This is a good question. What is the magnitude of the frictional force on the block? So that's what we need to find. So the first thing we want to do is we want to be able to draw this picture and look at everything. Okay. So let's try and give it a shot. First, so we have a block. Right. So the block will have. It says there's this force that is at a downward angle of 30 degrees. So it's going to go and look like this. And that's going to push on the block. So the idea is does the block begin to slide, or does it remain stationary? So we somehow have to solve for friction and decide whether it is going to be a static or kinetic friction, right? And we have this force of 12 newtons that's applied. Now, to draw all the forces on the block, we have to look here, right? We'll still have a force. This is just F. We'll have FG. We'll have Fn. And we'll have F. We'll have a frictional force. We're not quite sure what it is yet. So basically what we can do to answer this question is we have to ask ourselves, does the block begin to slide? So the only way to do that is to figure out if the static friction maximum is met, right? So that will actually make this easier. And this is, I think I alluded to the fact that you could get confusing problems before. You'll notice you're given the coefficient of static friction and the coefficient of kinetic friction. But let's look here. The question is asking, does the block begin to slide? Well, the theta angle is right here. Right? That's theta. You'll notice it says a downward angle of 30 degrees. You'll notice the question says, does the block begin to slide or does it remain stationary? So begin to slide, it's not asking if the block is moving or not moving, really. It's asking, does it begin to slide or does it stay stationary? So the question is F greater than, equal to, or less than Fs max. And I hope you can see right away that answering this question in particular will answer our will answer whether the block begins to move, and we actually don't need the kinetic friction to answer this question. And then it wants to know what is the magnitude of the frictional force on the block. So in order to do this, let's take a look at the nicer picture. You can see we have a nicer picture here. And you'll notice that they save us from a more complicated free body diagram. I want to draw the real free body diagram because they make it a little too simple, which I don't really like. Because they do next steps here and not a true free body diagram. Hold on, where's mine? All right, so the free body diagram from the picture, I want to do this in a different color. All right, we'll have our easy forces, Fg, Fn, F, and Fs. Okay? Now, the two vertical forces are pretty easy to see, right? That's where the normal force from the surface. That's Fg, of course, comes from gravity. Those are the easy ones. Now, this force was given in the problem, and it's a little hard to see. But you can see the angle theta. They did it here. I wrote it from here. It's the same angle, same thing. And they're going to break it into components and direction. So the first thing we want to do is we want to look at and see and choose an axis. All right. They take that step for granted because it's going to be a easy choice. But when you have an angle, you have to decide whether you want to rotate or not rotate. And you want to make that decision based on whether it makes your life easier. Right? So you can see that it's different than going up a ramp, right? Whereas the ramp sort of puts a lot of forces in only one direction. Here, oh, I lost my free body diagram. That's not great. I'll draw it again because it's actually good to see the process as many times as you can. So I'm going to redraw the free body diagram. So there's only 4 forces. Fg, Fn, Fs, and F. I'll just have to pretend that's straight. But what I wanted to get to was adding an axis to the free body diagram, and you'll notice that it selected everything for some reason. Hold on. You'll notice that if we make an axis, a standard axis, right? That wasn't great. But you'll notice most of our forces are in one direction and only one is in 2 directions. You're usually going to have to break something up into X and Y components. But because we're given the angle, we're given all the original stuff, it's not so bad. And then from this free body diagram, you'll notice they break it up further into 2 free body diagrams here. Right? So you have the X and the Y components. So they have X and they have Y. And there's 3 forces in the Y, 3 in the X. All right? And recall that Fx here will be F cosine theta, and Fy will equal to F sine theta. That's from chapter 3. Right? It's no big deal. Now, what I want to do is go back and get the see what's known and what's unknown. So we know F, we know M, we know theta, and we know the coefficients of friction. So 12, 8, 30. I'm going to try and memorize those. So we know that the magnitude of F is 12 newtons. We know that theta equals 30 degrees. And we know that M equals 8. We know mu S equals 0.7. And we know that mu K equals 0.4. But now what we want to do is we want to sum the forces in the X and Y direction, all right, given what we know. And I'm not going to plug in numbers, but I'm going to refer to what's here on top, what I've just written. So right here, if you see me moving the cursor, to know what's given and not given, all right, because I'm going to do this symbolically. So let's switch it up a little to a different color. And let's see here. Sum of the forces in the X direction will be equal to, let's see here, we have Fx minus Fs, and that will equal 0, right? So that could help us if the tell us that the Fs will be equal to the applied in the Fmax direction. But you'll notice the first question is, so that will help us with part B, because that would just be what it is. But we don't know if we've reached the maximum value yet, right? So the X direction will actually help us. We can say that the applied Fx will equal Fs, but we need to know, is Fs, how does Fx compare to Fs max? Right? We want to know if this 12 newtons will get us moving. So this gives you the answer to part B pretty clearly, because this implies that the actual value of Fs will be equal to F cosine theta. Right? And we have both those numbers. So we can get the frictional force. But we don't know if that frictional force is equal to or less than the maximum frictional force, right? Because this is just a number at this point. So let's go and look at the forces in the Y direction. Okay, so that's going to be equal to Fn minus Fg minus Fy, and that too will also be equal to 0. So that means that Fn is equal to mg plus F sine theta. And so why is this important? Because now we can compute Fs max it's going to be equal to mu s times mg plus F sine theta. And now we're cooking. Now we're in business, because now we have both values, right? We can look at we've calculated the maximum static friction, right? And we can then compare that with the actual value of the static friction when the force applied is equal to 12 newtons. All right, so you can plug all the numbers in and you can answer the question. And if you'll recall, the question was does the block begin to slide or does it remain stationary? So you have direct equations to answer that now. Basically, you calculate this number, and then you compare it, or you calculate the static friction that's actually in the problem, the maximum possible static friction, and you compare them. See what you get. You'll notice here that let me go to what is ms? Mu. This is the ms is the coefficient of static friction, and that's mu. It's supposed to be the Greek letter. I'm not very good at writing it today. Yeah. You found it on the typewriter. That's good. So yeah, it's supposed to be in US. So that's how you could compare whether once you have the maximum value, then again, this is just a number, right? You can solve for f of s, the actual applied static friction, what you're getting, because remember, if you're less than the max, you can always increase the force and then increase the static friction. But here we can get the maximum by using the actual expression. Remember, where did I get this whole thing? Fs max, the maximum value is equal to mu s times f of n. All right, we wrote that in the last slide. So that's where that comes from. Oh, that's fine. I have no idea what the numbers are. This is one of those times where, plug it in and find it out yourself. I'm happy with the answer as is. So I'll let you guys fight to see who got what. I went through a whole calculator error thing in the previous class, but you'll notice you have the mass, you have g, you have f, you have sine theta, you have mu s. So you should be able to figure all that out, and it should just be comparing the numbers. Well, there's two numbers to get here, right? So there's the maximum and the applied, and you have to understand something very clearly here. This fs is not necessarily this fs. You're comparing in the y direction, that gives you the normal force, and that lets you calculate the maximum possible static friction. The question is, are you at the maximum static friction, right? So you're saying there's a max of 60. If regular S will not be the same number. Okay, regular S you don't need to do, is just what it is. Remember, and remember the graph for how friction works. I'm going to draw simplified ones so that we don't lose all the work. That's fine. So remember, I'm going to do this in different colors. I'll go back to blue. First of all, this number will change as your applied force changes. This is the maximum that the number could be. All right, those two circled quantities are not the same necessarily. They could be, but they're not necessarily. And remember your graph for friction, right? I'm just drawing it here. So this is the time you're pushing. This is the force. Remember, this is where the static friction, and this is kinetic friction. Now remember, so basically what we're saying is that, right, you could, basically when we find the Fs max, we're finding this value. When we calculate, the other question is this Fs value, is F cosine theta, is it equal to the maximum value that I just drew on the graph? Or is it somewhere here on this line? All right. Regular S speed? No, static friction. Why do we need the Fs to solve it? Yeah, I mean, so that's the answer is Fs is not necessarily equal to Fs max. All right, your static friction, if you're getting, if the numbers I'm looking at are correct, it looks like 60 is the maximum static friction. When you calculate F cosine theta, you get 10. So you're down here somewhere. So basically, what's happening, to interpret the situation correctly, is that you're not, if the numbers I'm reading are correct and pertain to those, is you're not moving the block, right? You're just pushing down on it, and that's what that's saying. So you have to realize the question here isn't asking for numbers. You have to get two numbers to get to the answer, but the answer is, does the block move or doesn't it? Do you have enough friction? Are you at the maximum value of kinetic friction, of static friction, or are you at some value lower than the maximum value of static friction? That's the question. And so in order to do that, you have to compare the applied static friction to the maximum static friction. Okay? And you need to solve it to determine if this block is about to start moving or not. How close are you to make it start moving? That's the question. All right. Any other questions about this? All right. So to make sure I get this, the friction is static until it exceeds the max, then it becomes kinetic, right? Yes, that's true, Mina. Yeah. It comes up here. So if you push harder and harder, and then you get to the maximum static friction, and then you start moving. And then your friction drops to the kinetic friction. Again, I think the important thing to see is that the sum of the forces gives you, probably could have cleaned this up, but the sum of the forces gives you the normal force and the applied static friction. So summing the forces gives you one number, right? This is 12 cosine 30. That gives you the static friction in the problem. But once you calculate the normal force, which you also get from summing the forces, then I'm going to put this here so that it's clear. Then you have this next step where you can plug the normal force in, which is right there, right, to this part of the equation. And that's all we're doing. That's a separate step. This step here does not come from summing the, is not a direct summing of the forces equation. We do summing of the forces, and then we get our results. So from summing the forces, we get the actual value of Fs in the problem. That sounds like that's your 10 value. And then you can get use the normal force calculated from summing the forces to compute the maximum possible value of static friction. Okay? So the Fs is the Fs average till it becomes, no, it's not the F, it's the instantaneous SF. Notice there's no averaging here. Basically, it's saying that at this force, you're here at 10. There's nothing average about it. Once you, if you apply more force, you move up the curve until you get to 60. Then once you get to 60, you start moving. All right, good. Questions are great here because this is, you're welcome, because this is important for how you solve these problems. And again, the procedure is what's important, and unpacking the information is equally as important. Okay. So let us continue. We'll talk about drag force for a little bit. Drag force is basically the same as friction, but in the air. So we'll talk about air resistance. And in order to add air resistance into kinematics, the reason we didn't do it before is because we really need to have an understanding of how to add in forces. And without that, we can't do it. So we accomplish this determining drag force and terminal speed by looking at the gas as a fluid. All right, and a fluid is, at this point in the course, is defined as anything that can flow. And when there is relative velocity between a fluid and an object, there's a drag force. All right, it opposes relative motion and points along the direction of the flow relative to the body. Here we examine the drag force for air with a body that is not streamlined, for motion fast enough that air becomes turbulent, that is, breaks into swirls. Okay, so basically, I don't know. So basically, what we have here is if you have a falling body, right? You have this cat that's falling. The drag force will sort of act like a friction to slow it down. And you'll notice this sort of behaves a little like static friction until you get to the terminal speed. And the terminal speed is where the drag force equalizes the gravitational force, and you stop accelerating. Okay. Now I think I have. Do I have the example that I like here? I'm not sure. Yes. Okay. Good. All right. So you'll notice that the drag force is sort of complicated, and as I was pointing to the Physics 2 class, that occasionally, this starts to look like a chemistry class, and this is one of those first instances where we're dealing with densities and things like that. So the drag will depend on the drag coefficient C, which is this one here, right? The density of air, or the density of the fluid, the cross-sectional area of the object, and the relative velocity of the object. Okay? In reality, C is not constant for all values of V, but we are going to look at easy cases. Okay? And again, we can see how the drag coefficient is found out here. Now, you can just add drag like any other force. So, for a falling object, you'll notice that they've missed some steps here. You can sum the forces in the y direction, right? So you have drag pointing up minus Fg down, and once terminal speed is reached at V terminal, A equals 0. All right, that means you're falling, but you're not accelerating. And we're actually going to see how really important terminal velocity is in a minute. Okay, once the drag force equals that, we can plug this in. I always have to look up I do not have this equation memorized, and I don't plan on having it memorized. C rho AV squared. So we'll put 1/2 C rho A V squared minus mg. So when this V is V terminal, we're going to call that 0. And then I think you'll see if you do the algebra, they keep the mg as Fg here, fine, whatever. But you will see that if you just solve for V terminal, you will get this expression here. Okay? And that will be your terminal speed. So terminal speed can be increased or decreased by changing your cross-sectional area. And if you've ever seen skydivers fall, they'll shift their position to fall faster or slower. So they control the speed they're falling by just changing their cross-sectional area as they're falling. All right. So look at skydivers move, and you'll get an intuitive feeling for changing cross-sectional area. All right. I'm sure. Yes. Problem? What's the question? I think you, hmm? The 1/2 just comes from, no, this is 1/2, okay, I got you. This is just from the last slide. So this was my attempt, because I want to write it better anyway. This is just 1/2 C rho A V squared. Yeah, it's a C.
Okay, I got it. I'm so sorry.
No, that's okay. That's okay. So I'll write it again. I'll try and write it neater. It's hard to write neat with the pad, so don't be shy about asking for something to be clear. So that's 1/2 C times rho A V squared. I'll leave it as f of g this time, equals 0 when v is v terminal. Okay? And then you're just solving for v terminal. And that's algebra. No problem. Okay. So we want to talk about raindrops. All right? And we'll see here let me see, I want to see if I can't remember whether I gave away. Oh, okay, I do have answers here. Good. Okay. So we want to look at the terminal speed of a raindrop and actually see the role air resistance plays. And air resistance is generally not negligible. It can be for certain situations, but we'll see that it's easy enough to add in once we can use Newton's laws. And we can, right? We can get the acceleration and then put it in our kinematic equations, and we'll be able to include it pretty readily. But let's look here for a raindrop. So we have a spherical drop feels the force of gravity, F equals mg. That's not a big surprise. And we want to express this in terms of water density, right? How do we get the mass of a raindrop? So if we go forward, so the F of g will equal the volume of a raindrop, which we'll take to be a sphere, times the density of water, which you have to look up, times g. All right, so the volume of a sphere is 4/3 pi r cubed. The density of water is g, or the density of water is water, and g is g. So these are all known things. The only thing we'd have to do is sort of guess and estimate the radius of a rainwater drop. Okay, so see if take a minute and see if you can see how obnoxious it is to find that. See if you can find the density of water there. Good. 1 gram per cc. I think we're going to want the 997 kilograms per meters cubed because we don't use the CGS system. So you've got that. And then what would you think for the radius of water? What would you guess? For the raindrop? Yeah, it's not really given, but would you think it'll be a micrometer, a millimeter, 2 to 5 millimeters? Yeah, that's fine. You'll see here in the book we use 1.5 millimeters. And you can see here that we can solve for the terminal velocity. We have Fg. If this becomes sort of a big thing. But you'll notice the r cubed here cancels with r squareds, and it simplifies quite a bit. And we get 27 kilometers per hour, or 7.4 meters per second. Now, let's compare that. Let's say that the average raindrop falls 5 kilometers. All right? So if it falls 5 kilometers, let's compare this to the non-air resistance speed. That's what I want to do. So without air resistance, without drag, right, we have v v squared equals v naught squared plus 2a delta y, right? So we know our initial velocity squared is 0, and we know that, and if we say delta y is equal to 5 kilometers, right? Just from that far in the sky, we'll get v equals the square root of 2g delta y. Okay, so that's the square root of, the minuses go away because the even though a is minus g, the delta y is also negative. You start at 0 and you're going down. So down and down have to be consistently negative. So that'll cancel that, but we'll get 2 times 10. Well, 2 times 5 is 10,000. 10,000 times 10 is 100,000. Someone square root 100,000 for me. Yeah, no, not 10 to the 4th, 100,000, 10 to the 5th. All right, I'll go to my, it's gonna be 100 times root 10. So it's gonna be about 300 meters per second. All right, good, 316. So V will equal, here, will equal 316 meters per second. You know what else moves at about 300 meters, 16 meters per second? Bullets. So if air resistance weren't a thing, going out in the rain would be like getting little machine gun bullets of rain fired at you. I don't think you'd survive very well. But I want you to compare just how quickly terminal velocity is reached and the vast difference between the actual speed rain falls at, which is very manageable, and the speed it would fall at without drag. So we can see that drag over is very fast. So we can see that when we neglect air resistance, one of the things we take, that when we do that, we usually look at distances that are too small to really matter. 5 kilometers is not too small to matter if you're accelerating, right? It's quite a bit. So yeah, so C is the drag coefficient. All right, so you just look that up for air. It's just something you look up. It's like the coefficient of friction. It's material dependent. Okay. So I like doing this rain example because it's fun. It makes rain seem dangerous, even though it's not. It's not dangerous at all. Are there any questions about rain before we go on? Yes, I hear an exclamation point.
Hi again. Just
Hello.
to ask you on the denominator, right, of the solution, the density there shows rho A.
Right. So okay, good question. So remember in the terminal velocity equation, let me get my pointer up here. In our terminal velocity equation, it's the density of what you're falling through. So that's the density of air. All right. But when we look at the mass of water, when we try to find the mass of the raindrop, we do that in terms of the density of the water. All right. So the density of water is associated with the mass of the raindrop, and that comes in the FG term up here. But for our terminal velocity for the drag, because the water droplet is falling through air, that's where the density of air comes from. So this comes from the definition of the drag force, right? And this density of water comes from finding the mass of the water in terms of density and volume.
Got it. Thank you very much.
You're welcome. Any other questions? Anger? All right. So as we can see here, we have a list of terminal velocities and speeds. So you'll notice that a shot from a shot put has a very high terminal speed, and it reaches that distance in about 2.5 kilometers. The raindrop, you'll notice that we just studied, they give the terminal speed of about 7. Again, not all raindrops are the same. I think Daniel's observation of 2 to 5 millimeters is probably more appropriate, and so you'll notice they give 7, but you'll notice that it reaches 95% of that speed or that distance in 6 meters. So basically in 6 meters, you're going to get to 95% of your terminal velocity. All right, so 6 meters isn't very far. You can look at tennis balls and baseballs. All right, that's pretty high. And a skydiver, typically a person falling, has a terminal velocity of 60 meters per second, and it takes 430 meters to get there. So terminal speed, remember we're talking about drag. So terminal speed is the maximum speed at which you'll fall through the air. Where this is drag pushing you back up. So this object is falling down, and when you're at terminal velocity, you are falling at constant velocity, right? So when v equals vt, ay net equals 0. Okay? Yeah. All right. Good? Okay. So now we're going to move on to the second half of Chapter 6. Terminal speed is a nice sort of bridge. And then we have uniform circular motion, the fun stuff. Okay. So recall that if you're moving in uniform circular motion, your acceleration is equal to the speed of, so let's draw a circle and let's talk about it again. I'm going to draw a circle. Oh, that was not a circle. I'm going to clear all. I'm going to make an ellipse up here. And we'll move this down here. So if we're moving in a circle, remember where our speed will be constant, but our velocity will be changing constantly, right? Because its direction changes as we go around the circle. But if we move around the circle at a constant speed, we call that uniform circular motion. And the acceleration will always point. Does anyone remember where the acceleration points in the uniform circular motion? Yes.
Towards the center.
Towards the center, very good. So we go towards the center, wherever we are. Okay? So that gives us the direction, and this gives us the magnitude of the acceleration. All right? So, and this will call a, this force, when we look at this as a force, right, we'll call this a centripetal force. All right? And I'll let you read those examples on your own. I'm not going to. Those are just talked about examples. Did I miss something? Yes, I did. I want to sort of get to it right here as the centripetal force. You'll notice it's not a new kind of force. It's the application of a force. Yes, Mina.
Question. So, just to make sure, centripetal motion is the same as it's always uniform. Circular motion
Yes.
is the same thing. Okay.
Yes, and I don't want you to confuse centripetal force with centrifugal force. Centrifugal force is fictional. You only feel it when you're in something. Like if you're in a car rotating, You feel like as you turn, you feel like you're being pushed to the edge of the car. So from inside the car, it feels like there's this force coming from nowhere pushing you. But if you analyze that same situation from outside the car, it's simply the car pushing you along with it, right? So the centripetal force is present in all inertial reference frames. The centrifugal force is not, which is why we call it fictitious.
Gotcha. All right, thank you.
So yeah, no, you're welcome. So the centripetal force is just the application of adding multiplying the force times the acceleration. I need to get to my times the centripetal acceleration. All right, so you add the mass to it that you put on a rock, and you can figure out the magnitude of that force. Okay, so if you put a puck on a string, the tension supplies the centripetal force necessary to maintain circular motion. So here you could see that the tension in this particular problem would be equal to mv squared over r, because that force would be keeping the puck in that uniform circular motion. I didn't do it quite well. All right. So what I want to do is I want to take a break, but I'm going to put the checkpoint up, which we will discuss when we get back. We'll read it now, and then we'll discuss it at about 12 to 15 after. So as every amusement park fan knows, a Ferris wheel, or think of the Eye in London, which is a big Ferris wheel, is a ride consisting of seats mounted on a tall ring that rotates around a horizontal axis. So if you don't know what I'm talking about, Google the London Eye on the break, and you'll get an idea. When you ride in a Ferris wheel at constant speed, it wants to know the directions of the acceleration and normal force on you from the always upright seat as you pass through A, the highest point, the lowest point of the and the lowest point of the ride, and then it wants to know how does the magnitude of the acceleration at the highest point compare with the acceleration at the lowest point, and how do the magnitudes of the normal force compare at those 2 points. There's a lot of word vomit there, so be careful. Okay, and I'm gonna get a drink of water, and I will be back at about 10 after and work on this, and we'll see what we come up with, or take a break and work on it. We'll work on it for a minute or two after we start again. Okay. All right. I'm gonna go away. Okay, everybody, ready to come back and go all the way through? Criminy, I forgot. That's okay. Oh, I have my iPad. I can take a picture of the attendance. I'll have to update that at some point. Probably one of my many tasks during spring break. All right. Where's the? There we go. Okay. All right. Okie dokie. You get a cough drop. Have a cough drop. Okay. So I hope you looked at pictures of the Ferris wheel if you did not find one or didn't know what it looked like. But basically, we can think of it in terms of the shape of a circle. Oh, I like big circles, but I don't want to get too big. Okay. Let's move you here. And so you would go around and you'd be sitting upright at each point in the circle. So let's look here. Let me go back to the chat so in case questions start coming up. Let's look at the two things we are comparing here. You'll notice if you read through, it's asking for either the magnitude of Fn or the acceleration. We want to be really careful about not getting these mixed up. I say that because getting things mixed up sometimes is par for the course. So the first thing it asks for is it wants to know what are the directions of your acceleration and the normal force on you as you pass through the highest point. So that's A. So the highest point would be here, right? And if we draw this, we have the normal force going up. That's Fn. But the acceleration, remember we're in uniform circular motion, the acceleration points down. Okay? So now what I want you to do is try and do part B. Of course, I did the easy one and you have to do the hard one. So, you know, some things will never change. But what direction would Fn point at the bottom here? Well, since you have a question mark, both go up. Yeah. So the normal force, remember you're sitting upright in the seat. So if that's true, the normal force has to be up. Right? But the acceleration always points towards the center of the circle, so that must also be up. So let's see what C is asking first before I look at the answer. How does the magnitude of the acceleration at the highest point compare with that lowest point? Good, Nicholas, very good. The acceleration, in order to be in uniform circular motion, the acceleration has to remain the same, right? Okay. So, so for C, the acceleration's for C, A is the same. Now here's the fun one. How do the magnitudes of the normal forces compare at the 2 points? So basically the top and the bottom. This is the fun one. This is the one we've been getting to. We've been wanting to get to. So we got the magnitude should be the same as your mass hasn't changed. Same. I don't know. Try doing the analysis. D, we're looking at D. So what I want you to try and do, if you're going around here, is look at both the top and the bottom and sum the forces. G does not change. G is always G. But we're not really talking about G right now. We're talking about the normal force and the acceleration. Although G will be important. So again, Nicholas, this is where you can't just, you're making the mistake of quoting the end result and just using it. You need to derive it for each point here by summing the forces. Fn, this is true. What you've written there works just fine when you have a flat space moving, translating linearly. We have uniform circular motion. You have to rederive the equations. Don't be afraid to summing the forces Everyone's got to sum the forces here. You can't be afraid of doing this because looking up the equations is not going to help. Deriving the equations will. We're going to do it. Don't worry. I want you to try and do it and see if you can come up with the answer. Because right now we're all over the place as far as the answer to part D. I just want to give you guys another minute. Yeah, no, I can give you 2 minutes, 2 minutes more. I'd say prove it that F top is greater than F bottom. Or the normal force at the top is greater than the normal force at the bottom. So again, as long as your equations show that, but we will, of course, see if that is the case. Mwahaha. Okay, so we seem to get consensus now. So let's check. So we'll sum the forces at the top. Sum of the forces. It's going to equal, right, Fn minus mg, and that's going to equal minus mv squared over r. So we can say up here that Fn equals, so this is at the top, equals mg minus mv squared over r. Okay? So that's the top. At the bottom, we can sum the forces equals Fn, still minus mg, but here it's going to equal just mv squared over r. This implies that so this is Fn top, that Fn at the bottom is equal to mg plus mv squared over r. So looking at the two numbers, Fn bottom will have to be greater than Fn top. Well, look at the circle. Are you pointing up or down? You can't solve. You can't set. So okay, Mina's gonna. This is good because this is going to be a common mistake, right? So you have to. You can't just automatically go through. You have to ask yourself in each question why the acceleration is equal to 0. So here we're in uniform circular motion. That should tell you right away the acceleration is v squared over r, right? So it can't be 0. So that's so you wanna, if you find yourself in that boat, you want to ask yourself as soon as I go. You should always ask yourself, if I'm using Newton's laws, what is the acceleration and why do I think it is what it is? Right? Because if you do that, you'll go, what's the acceleration? If you go 0, ask yourself why it's 0. And when you look at it, you should come in and say, well, it's moving. You might say the speed is constant uniform circular motion. But then you can see we have these acceleration vectors. And when you look at previous pictures, you'll see the acceleration vectors. That should give away that the acceleration is not 0. Okay? And then when you ask yourself, well, I'm in uniform circular motion, is there an acceleration for uniform circular motion? You can say, yes, there is, right? That in uniform circular motion, so I'll call it uniform circular motion, A equals v squared over r. And again, you just look at, you make the points at the top. These aren't really free body diagrams because they have acceleration, but they serve a similar purpose. You make an informative figure. So the acceleration is pointing down, Fn points up. The acceleration is pointing down, it's got to be negative. You can't call gravity negative here and then say the acceleration is positive. That doesn't work. You have to be consistent with your directions. You can't be afraid of those negative signs. Okay? So I want you to go back and look at your work and see if it makes sense, see if you can figure out what you did wrong, and then see if you have any questions. All right, just let me, I'm just going to ask if there's any questions, and I'll give you a minute. Okay, any questions? Because I'm going to move on. We're good? Okay. All right, so let's move on to a similar problem, but and we can check our answers that we're, physics is sane. I'll just leave that paused for a second, and then going forward, we're actually going to look at a similar problem, right? But now this time in the loop, you'll notice we're going to be on the inside of the loop going around the loop-to-loop, okay? So in 1901, circus performance, Allo Daredevil Diavolo introduced the stunt of riding a bicycle in a loop-the-loop. All right, so he's looping the loop. Oh, no, sorry, I did that wrong. He's coming down here and then looping the loop, okay? Assuming the loop is a circle with a radius of 2.7 meters, what is the least speed that v that Diavolo and his bicycle could have at the top of the loop to remain in contact with it there? All right. So now this is an interesting problem because at the top of the loop, right? Well, let's go back here because they just gave away everything. I thought I did that one a little differently. Let's talk about what we're going to see and why things look the way they look. So now, if you're going here at a loop, right? You'll notice that with the picture, at the top of the loop, which is our area of interest, he is just about to, he wants to come over, and he's got to just clear the loop, but you'll notice he's on the inside, not on the outside like the last one. So in this example, f of n is going to be down. Now, we're also going to have mg down, right? And then our net acceleration, and so that's our free body diagram, unless anyone else can think of any other forces. I don't think there are any. Does anyone see any? Okay. So what's going to happen is we'll sum the forces here. So minus Fn, right? Minus mg equals minus mv squared over r. Okay? Because it's, again, he's moving in uniform circular motion. Now, besides all the minuses, which do cancel mathematically, we have one more observation to make. If you're going around the loop and you're just about to fall off, but you keep going around, what's going to be the force of the surface on you? What is that normal force going to be? Anyone want to take a guess? 0. Good. And if we have that equal to 0, well, you notice we have quite a nice solvable equation. The m's will cancel, the negatives will cancel, and we'll get v equals g times r to the 1/2. All right, so let's take a look at a nicer presentation of it. You'll notice they have the free body diagram here written very nicely, right? But you notice there only are those two forces. And again, at the top of the loop, minus Fn equals minus mg equals mv squared over r. But Fn is 0 because when we get to the top of the loop, right? When we get to this top of this loop, we want to know the minimum speed. So what the minimum speed indicates is that at the top of the loop, where we would fall off if we didn't have inertia taking us over, all right, getting us to the other side of the loop. So here you go, and you're just about to go fall off. And if you were stationary, you would, but he's not stationary, so he keeps going in constant circular motion around the loop. Yes, Fn is only 0 at the top of the loop, right? But again, we have that question, right? So at that point, we can cross this out. So I'll do that again. Crossing out things is fun. We can cross that out, and then we solve for v, which is where this expression comes from. Okay? And you just plug in the given radius. You know g, and you get 5.1 meters per second. Okay? We're all good on that example? Good. Okay, so all right, so we're going to look at another example here, okay? We're going to look at solving for an unknown force in terms of known forces. So here we have this figure represents a Grand Prix race car with a mass of equal to 600 kilograms, all right? As it travels on a flat circular track that has a radius of r equals 100 meters. So because of the shape of the car and the wings on it, the passing air exerts a negative lift force downward on the car. So the coefficient of static friction between the tires and the track is 0.75, and we're going to assume that all the forces on the 4 tires are identical. All right? So if we look here, we have the free body diagram of the situation, right? We're going to put the car at this point on the track. This is a bird's eye view, and we're going to look at a cross-center version of the track. So basically, if you're looking at this right now, the car is still moving in a circle, but it's going to move sort of into the plane and out of the plane, sort of like this. You can see my hand in the camera. All right, it's not going to be a bird's eye view. You're not looking up, down at it anymore. You're looking at it. And we're only going to do the analysis because of the symmetry of the circle. We'll do the analysis at a point where things are just easier for us. All right, so you'll notice that you have your normal force, your G, your gravitational force. The lift keeps pushing the force down, or the negative lift rather. And then you have the static friction and the acceleration. Now, this is going to be a little confusing. You might be saying, well, wait a minute, Professor Toland. And again, I feel like I've lost referring to myself in the third person. But you might say, this car is moving. How can it be static friction? Well, it's the static friction. You have to ask, what is the friction doing? The friction is preventing the car from changing its radial value, right? It's acting in the radial direction. So because the car has a constant radius and moves in a circle, the friction is indeed static. You are not moving in the radial direction. You have a speed, and your angle certainly changes, but your radius does not change. That is very important. And that's the direction in which we're applying friction. Okay, so we're still consistent with our definition. So let's take a look here. Before we even answer, we ask a question. Let's take a look at let's set up the equations first, because it doesn't even matter what it's asking. We know we're going to have to do that. So let's look here. So looking at this, we have some of the forces in the x direction, right? If I just look at that, that will be equal to minus Fs, right? And that's just going to equal minus mv squared over r, right? Not really, no, because the car is still moving smoothly. With drifting, you sort of lock everything up and you move around the corner. The car, I think, would still be. I mean, it looks like a drifting problem because we're not considering the rolling of the tires, but in drifting specifically, the car would be locked. Yeah, Mina.
So, Professor, just to reiterate. Kinetic friction is considered a friction where there is only change in the distance.
Well, kinetic friction occurs when an object is moving, right? And again, you have to ask yourself in this particular situation, where is the motion happening? So the static friction is in the radial direction. You'll notice this is r versus y. And the car is moving in a circular pattern, r is not changing. So if r is not changing in that axis, you're actually not moving in r, right? You have an angular value that you're changing, but you don't have an r value you're changing. The circle's not getting bigger or smaller. So in that sense, you actually aren't moving, and you have static friction in r. You would have kinetic friction in theta, but we're not working in theta.
Right. So as long as there is change in distance along the direction of the friction, that's when we have kinetic friction.
Right.
Okay.
Remember, the friction has to oppose the motion.
Got it. All right. Thank you.
You're welcome. So we want to write this. We want to continue writing this equation. Yeah, the r is the radius of the circle. So if we make a circle, that's not a circle. Hold on. It's not clear here because we're just looking at a circular section, so I'll make a circle. It's the radius of the circle. So if we make a quick circle, and we move that circle here, good. Let me. So R is the radius of the circle. Yeah, big R, small r, doesn't matter. You just have to look at your context. Yes, Mina.
I'm sorry. I think I just want to elaborate on the R. There is a confusion because you annotated as a small case R.
Right.
While on the
The problem, I get where, yeah, no, I get where the confusion is. What I'm trying to say is it doesn't really matter. You can say in this case R is equal to big R. It's fine. You have to become used to context. You can't be married to any one interpretation of anything. So one of the things we do, and one of the reasons I change subscript sometimes, is it's to get used to reading this stuff. You have to break away from saying one of this is this thing and it's always this thing and you can't change it. Little r, as long as I have the context here that little r and big R are the same thing, it shouldn't matter. So, but if you'd like, because we are still learning, I will amend my R here to big R, but it really doesn't matter. So, because they're calling little r the axis, but we're not going to use that information. So anyway, what we have here is that this is equal to mu s times Fn is equal to m v squared over r. Well, that's supposed to be an m. Okay, so actually I'm going to clear this and write this a little better. So let me just write this again. Forces in the r direction is going to be equal to there. So that restricts little r now. Minus fs right, and then this will imply that mu s times Fn equals m v squared over r. Okay. So now the next step then is to sum the forces in the y direction. Okay? And that's going to be equal to Fn minus FL minus mg, and that will be equal to, you'll notice again, that will be equal to may, but the car is not moving up and down on the road. So we can set that equal to 0. Again, I set it equal to 0 because I can look at the motion and understand what's happening with the motion, right? That's all that's going on there. So because of that, I can set that equal to 0. So now that we have our equations, let's see what they want us to do. Not that we'll be able to save those equations, but I'll be able to write them down. So A, if the car is on the verge of sliding out of the turn when its speed is 28.6 meters per second, what is the magnitude of the lift acting on the downward car? Now, recall, just because it'll slow us down a little, we can recall that mu naught, the static friction, times Fn is equal to m v squared over r, right? And this implies that Fn equals mv squared over mu s r, right? We know m, we know v squared, right? It's given here. We know mu s and we know r. So we are able to find Fn. And that's important because you'll also recall that Fn minus Fl minus mg equals 0, right? And so we know that this implies that Fl equals Fn minus mg, okay? And that implies that Fl equals m v squared over mu s r minus mg, okay? All right, so we now have an equation for the lift. But now what I want you to work on, I want to see, this is one of those things where you have to like pull stuff out of your hat. So if you look here, the magnitude FL of the negative lift on a car depends on the square of the car's speed. We can see that right, we can see that directly right here, right? We just derived this expression. So just as the drag force does. So thus the negative lift on the car here is greater when the car travels faster, as it does on a straight section of track. So if we're on a straight section of track, what is the magnitude of the negative lift for a speed of 90 meters per second? All right. So I want you to try and see where your starting points are to come up with it. Try and think through it. Where did I find USFN? Remember, this is all from previous work. We found all of these equations by summing the forces in the radial direction and summing the forces in the y direction. All right, and remember, if you remember from the free body diagram, there's only the static friction force here that was in the minus direction, and then equals minus mv squared over r. I canceled the minus signs and did some math, but that's it. All right, and the car is on the verge of sliding, so that means we're using that maximum friction, that maximum static friction. Okay. Yep, no problem. So how would you start this one? I'll give you another two minutes to think about it. It's very easy to do, but it's very tricky because it's not a skill we've practiced a lot. Oh, that's you're on the right track, but we want to know how, basically here's what we have, right? We know our speed here and all the stuff we knew before that's given, and from here we found FL. All right, down when the car going on a circle. So now we want to know the magnitude of the new FL. If we see that FL, the lift force, depends on the speed squared, right? So basically what they want to know is on a straight section of track, you should have greater lift, right? So we want to know what we want to know directly actually what the new lift force will be. Or we could call this, if you want, FL flat. If you want to differentiate them. I'll take away this whoosh mark here. So M is I'm just gonna go see if I can look back and tell you. M will be 600 kilograms and R will be 100 meters. Yes, Vina.
I'm sorry, Professor. Just because I got confused, I just want
No,
to
good.
know.
That's okay.
We're not solving it as in going in a flat, like straight course. We're still
We
solving
are.
it as it does in a curve, right?
Well, in part A, we're solving it in a curve. In part B, we're solving it on a flat surface.
I'm confused. I'm still confused because either A or B, the surface is flat. It's just the trajectory of the car.
So I think you're trying to fit a round peg into a flat square hole to make a bad joke. Uh, so in part A, you're looking at the lift, and you get that from solving it from going around in a curve. In part B, you're going straight. There is no
Okay,
curve in
that's
part
what
B.
I was. So it's the trajectory of the car is different.
Right.
That's what I was, okay, that's what I
So
meant.
the trajectory of the car is different in both of them, but we're looking at this lift force. Okay.
All right. Thank you.
No problem. US is 0.75. Coefficient of static friction. Now you want to be careful if you try making that r into infinity for a straight curve, things don't go well, right? It's not helpful. All right, so you're ready to see some physics magic? This is where mathematicians get angry because you have to use completely physical arguments to solve this problem. The math doesn't work, but we manipulate mathematics in a way that would drive most mathematicians nuts. So let's go back here to our equation, all right, for part A. If you make it into a straight line, that doesn't work. What you'll notice here is that FL is proportional to V squared. And as V squared gets bigger, it's the dominating term, right? So what we're given here is that FL will always depend on the square of the speed, okay? So what we can say is that the ratio, to get rid of all the stuff we don't know, we can look at FL flat over FL from part A. We can actually set that equal to the ratio of the speeds, right? So FL flat is going to be 90 meters per second over 28.6 meters per second. And so we'll see that if we multiply this out, this implies that FL flat equals which is greater than 1, certainly, and then FL from part A. Okay, and we can see here that that speed will get bigger. Yes, Mina?
All right, so the first thing I noticed is that this should all be squared because, right? Or
No, that is incorrect. If FL is proportional to V squared, we're
okay.
canceling that, in a sense, we're canceling that dependence. Oh no, wait a minute. Yeah. No, you're right. It's V squared. I'm being silly. I'm tired.
No worries. Okay, first,
Yeah, no,
first
you're
thing
right.
I
You're
noticed
right.
is that's what I was
You're right.
curious.
I was thinking about it. You're right. So it's the square root of the velocities over each other. That's fine. That's okay.
It's definitely for the part A. I understand that, which is the denominator, right? Or which one is it? Yes, because the no,
Yeah,
the one
it's
on top.
proportional to the square of the velocities. So that means we can take the ratio of the velocities. I was just looking at that, thinking what I was saying didn't make sense. So what I was thinking, I'll let you know where my mistake was if you want to look, if you want to know. I was thinking of taking ratios and the v squareds canceling out, because usually when you take ratios of complex functions, but I forgot that the whole point of taking the ratios is that if this is true, then, and we also know that FL flat, or FL flat, is proportional to v squared,
It should be the
then the
same.
ratios will be the square of the velocities, right? We take these two ratios, that's got to be the v squared over the v squared. So that's correct. I messed that up.
Yeah. That one would, so it would be, to my understanding, right? It would be that case if the velocity rate was the same. We would be able to do that, right?
So I want to be very careful here with the language. So when we look here, this is for a flat, straight track.
Yes.
This is for a curved track. And these are for fixed velocities. And I realized I was wrong when I started increasing the velocity and realizing that in my what I originally wrote, that don't work, because again, we wrote this up here, right? It's proportional, and I'm going to delete this square because that was just to make this hash mark, that was just to make a point of where I messed up, because I was doing different algebra in my head. which is fine. That happens. But the whole point here is that FL is proportional. That's what that alpha fish means to V squared, right? And that's the whole thing. So V has to, so as V goes up, the lift force has to increase with the square of V. And that's where I realized I'd erred down here. But that's it. The velocities are both constant in these problems. They're not changing. Or not the velocities, I'm sorry, the speeds are constant in these problems. Okay?
All right. And a second question, I'm sorry.
No, you should ask as many questions as you like.
All right. So the FL for the bottom, right? The one is actually on the fraction of the top. If we were to use, because we know that for the part A, the curve, FL equals mv squared over the radius minus mg, right?
You forgot the mus, though. You forgot the coefficient of static friction.
I'm sorry. Yes, and this one.
Yeah.
In the denominator, would it be the same thing? Because essentially it's straight. It's not curved.
If you change it to straight, this is for a curved surface. If you change it to straight, r becomes infinity, and you're no longer proportional to v squared. So you ruin the result of the problem, because if you turn this into something straight, you're basically what you're doing is you're making your solution. You can't change things at this level. You really have to change things at the summing of the forces level, and then you'd have a different type of acceleration, right?
Correct.
So you can't just modify the solution to make it fit. That's not going to work, because then everything goes a little haywire. What they're doing is they're telling you that it's hard to solve this on a straight track, so you can actually use it with the ratio of what you get on a floating track or on a curved track, which is easy to calculate, and that opens the door to calculating something quite simply of something that would be very difficult to calculate otherwise. Yeah, that number looks right. Does that make sense, Mina?
No, I think I'll have to work it on my own a little bit, so I won't take more time from anybody else, because it seems that I'm the only one having this question.
Well, no, probably other people have it, but let's I mean, this is where I wanted to stop. So we're not moving forward from this today. So this was my intention. We still have 10 minutes or 8 minutes. So again, what you cannot do, you cannot just make this straight. If you do that, you see where I'm pointing the equation up here?
Yes.
If you make r equal to infinity, that's what you essentially do to make it straight, and then this term goes away. Right? Now you might argue that v goes faster, but you can't get v to be infinity. The maximum v could possibly be is the speed of light, but in a straight turn, r is infinity. So c squared over infinity is still 0.
I understand that, but that's so this part I understand, and I wouldn't use it, because in a diagram of forces, where it's completely, I feel it's completely different for B.
Yeah.
If you compare it from A, so
right.
I feel like the FL is completely different if we have to analyze it.
That's exactly right. That's exactly right. It would be. What the problem gives you is it says that the magnitude of it on the flat surface is also proportional to v squared. So what you're given essentially down here is that what the problem is basically, so all the information it's giving you is it's saying that FL flat is also proportional to v squared. That's it. This is the new given information. And then once you have that information, you can make the ratio.
Professor,
of the
for the sake of last effort to understand it, would it be possible for us, if you can help us create the diagram for B only to see how?
So that's the thing, is the diagram for B is hard. So the whole point here is that you can't actually, is that it's solving for the FL90 is very difficult without the circular result. So the idea here is that the circular is I mean, I can draw it for you, but it's just a car moving in a straight line.
Yes.
And it's a car moving in a straight line through air. So diagramming it is a little complicated because, again, you'd have to have the air resistance and all that stuff. Whereas here, what they're basically saying is you can just use the previous information to get the lift easily instead of more difficultly. So in a sense, there is no diagram for part B, is what I'm trying to say. Or that's useful. Basically, you can't, solving this equation for part B without part A is very, very difficult. And when I mean difficult, I mean probably beyond the scope of the course. So it's not an equivalent problem, right? What we're saying is you can take advantage of the fact that it will also be proportional to V squared, and then make a hard problem an easy problem. That's what we're really doing in part B. Okay? And if you want to visualize it, again, it's just a car moving through air. Like it's going along a straight line moving through air. There's not a terrible amount to diagram. Okay?
Yeah, all right.
Okay. So I think that's good enough for today. I'm going to stop the recording. And so keep in mind, again, the exam is on Tuesday, April 21st. You'll have one that kind of quickly follows in mid-May, probably on the 19th. And then after that would be the final, during finals week. And since I'm doing the finals online, I don't want to overload you with final exams. So let me know what day your other finals are, and we'll try and accommodate as many people as possible. Okay? All right. I'm turning off the recording.